Electricity. Lecture number 2. So, coming to the introductory part of this particular lecture. In this lecture, we will be dealing with the factor affecting resistance, resistance in series, resistance in parallel, and a basic concept of power. Okay? So, let's move on to our first topic in this lecture. Factors affecting resistance. So, apart from length, area and temperature, resistance actually depends on the material of the conductor. This property is called as resistivity and it is denoted by rho, the Greek alphabet. So, the overall relationship is mathematically written as rho equal to R equal to rho L by A. Please remember this formula. Now let's move on to a resistance in combination. So if we have any given electric circuit, there can be any number of resistance, and in general there are two possible combinations. They are series and the other one is parallel. Now let's first look at the series combination. So if we have a resistance in series, as the name suggests, in this particular case we have all the resistances arranged in series. That is, they are arranged one after the another. So a series resistance are connected across the two ends of a battery. Please have a look at the diagram. In this case we have considered only 3 resistors. Okay. There can actually be any number of resistors. Let it be 100, 200 or your wish. There is no limit. So whenever we have a series connected resistors, the potential will be divided across each resistor separately. Note that in a series connected circuit, the current will be same in all the resistors. Okay. So the voltage across each resistor according to Ohm's law will be, for the first one it will be I into R1, for the second one it will be I into R2, similarly for the fifth one it will be I into R5 and so on. Okay. Now that the I current is same in all the cases, so I'm repeating this again. The voltage across each of the resistor will be different, provided the values of R are different. And we also have that the total sum of the voltages, individual voltages, will be equal to the voltage of the battery, right? So from the formula of V equal to V1 plus V2 and so on up to Vn, and by Ohm's law I get this equation. So on cancelling all the I in the above equation, I'm left with this particular equation. This is the equivalent resistance. Now coming to the resistance in parallel. So as the name suggests, here all the resistors are arranged parallelly. A diagram will actually help us understand better. Okay. So if you observe a bit clearly, here all the ends of the resistors are connected together, and these ends are in fact connected to the battery's ends. Okay. So in any parallelly connected circuit, the voltage across all the resistors will be the same. Okay. So by Ohm's law, the current will be different across each of the resistor. Okay. Hence, if we proceed mathematically by Ohm's law, the current in the first resistor will be this, and the second one it will be this. Similarly, in the sixth one it will be this, and so on. This is just simple Ohm's law equation. And since I have I equal to I1 plus I2 plus so on up to In, because the net current is getting divided, and by Ohm's law, I have this equation. So on cancelling all the V, as all the V's are equal, I'll be left with this equivalent relation. So this is the equivalent resistance for a parallelly connected circuit. Now let's solve some examples for a better understanding of these formulae. Okay? So here we will be discussing 4 practice problems, 2 on series combination and 2 on parallel combination. So let's start with the question number 1. So you have to find the equivalent resistance in the given circuit. You have 3 resistors R1, R2, R3 of given resistance values. So as you can see that these 3 resistors are in series connected. My formula will be this. So on substituting the values, I get R equivalent to be 22.5 kilo ohms. K means 1000 kilo. Now let's go to the second problem. For the same question, I use a different circuit. The values of R1, R2 and R3 different this time. Here again, R1, R2 and R3 are in series connected, which is obvious. So I use the given formula, and on substituting the values of R1, R2 and R3, I get R equivalent to be 18,000 ohms or 18 kilo ohms. Fine. Now let's solve 2 problems on a parallelly connected circuit. For the same question, consider the given circuit. Here my R1 is 1, R2 is 3 and R3 is 2. As you can see, these 3 resistors are parallelly connected. Note that all the ends are connected to the battery. So I use this formula, and on substituting the values of R1, R2 and R3, I get 1 by R equivalent to be 11 by 6000. So my R equivalent will be the reciprocal, which is 6000 by 11, which is 545.4545 and so on. Now let's solve another problem. Here again I have a similar circuit with different values of R. So again I have 3 parallelly connected resistors. So I'll be using this formula again, and when I substitute the values of R1, R2 and R3, I get 1 by R equivalent to be 16 by 1000. Sorry, 16 by 10,000. So my value of R equivalent is 625 ohms. Fine. Sometimes we may come across a circuit which has a combination of both a series and a parallel combination. So such circuits are actually very easy to solve. Don't worry about them. So just solve them in the above 2 methods illustrated in the previously discussed 4 problems. They are quite simple. So for your better half, I'll be solving another question. Let's have a look at this one. In this question, I have the 6 ohm and the 3 ohm to be parallel, which is in series with the 2 ohm. Okay, as the 6 ohm and 3 ohm are parallel, so the R equivalent to that part will be 1 by 6 plus 1 by 3. So on solving, you get R equivalent to be 18 by 9, which is 2 ohm. Now this new 2 ohm and the old 2 ohm are in series. So by using the formula for a series equivalent, I get the R equivalent for the entire circuit to be 4 ohms. So let me solve you another problem. So here I have 2 resistances in parallel and 3 in series. So for the parallel part, the equivalent resistance will be given by 1 by 6 plus 1 by 12 whole inverse. So for the parallel part, which is 6 and 12, the equivalent resistance will be 3 ohms. Sorry, it will be 4 ohms. Now, this new 4 ohm and the old 3, 6 and 5 ohms are in series. So my overall resistance will be 18 ohms. Fine. So for your benefit, I will be giving you 3 homework problems. Question number 1, 2 and 3. Find the equivalent resistances for these given 3 problems. So this is your first question, this is your second question, and this is your third question. These are actually quite simple and straightforward, and these are the answers for your benefit. Please check them accordingly. Now let's move on to the last part of this lecture, which is power. The power consumed in any circuit mathematically is the product of the V and I. Okay? So there are many other equations which can be simply modified by substitution. So the unit of power is given by watt, W. 1 watt equals to 1 joule into 1 second. Another unit of power is a kilowatt hour. 1 kilowatt hour equal to 746 watts. So let's solve a problem on the concept of power. So I have a question in which you have a bulb connected to a 220 volt generator and the current is 50 amperes. What is the power? So by using this formula, I have the value of V to be 20, I to be 50. So power will be 1000 joules. Please change the question, it's not 220, it's 20 volt. And this is the end of the lecture. Thank you for watching. I wish you good luck.